All right, let's do a few more examples in 12.3 talking about chain rule. Hopefully you understood all of the examples we did in example number 1, because it looks like here we're going to get a little more challenging. I don't like to call it harder. I like to call it funner, right? All right, look at example number 2 with me. It asks us to differentiate. So it gives us a function, 4x times 3x plus 5 to the 5th power. Now I need you to be careful. I need you to look at this really carefully and think about what derivative rules you are going to be using here. If the problem was just a 3x plus 5 to the 5th power, this would be just a regular chain rule. I could bring the 5 forward, I could keep the inside the same, I could subtract 1 from the exponent, and then take the derivative of the inside. But it's not just a 3x plus 5 to the 5th power. And if it was just a 4 out in front, I could actually just leave that 4 alone, then do the chain rule with the rest of my problem, and then bring the 4 back at the end, right? My constant rule. But it's not just a 4. Hopefully you noticed that you have a variable being multiplied by something with another variable. Hopefully you notice that this is actually a product rule. Now, there's also going to be a chain rule in it, because in order to find the derivative of this piece, we're going to have to use chain rule. So this is actually multiple derivative rules in one. It's a product rule and a chain rule. Are you ready? Let's start off with product rule. Remember product rule? Product rule says the first times the derivative of the second. Well, now in order to be able to take the derivative of 3x plus 5 to the 5th, that's going to be a chain rule, right? So if you have a chain rule inside your product rule. I'm going to bring the 5 forward. I'm going to keep the inside the same. I'm going to subtract 1 from the exponent, but then don't forget to multiply by the derivative of your inside. So that was your first times your derivative of your second, plus your second times the derivative of your first, and the derivative of 4x is just 4. So there's my product rule with a chain rule inside. I can go ahead and simplify a little bit in each term. I have a 4x times a 5 times a 3, so I could really say 60x times that quantity 3x plus 5 to the 4th power. Plus, I can put the 4 as a coefficient and say plus 4 times the quantity 3x plus 5 to the 5th power. Now this isn't as factored as you could probably get it, but for right now I'm okay with you leaving your answer like this. But later on, we're going to have to make this look a little bit nicer, because we're going to want to solve for x. We're going to want to take this derivative and set it equal to 0. But for right now, I think that was enough to handle with a product rule and a chain rule. All right, let's look at B. What do you notice in B? Ooh, hopefully some of you noticed that radical, right? And as soon as I see a radical, I know that I'm going to change that into a fractional exponent, a rational exponent, right? If you notice the quantity underneath here, 1 minus x squared, is really raised to the 1st power. My radicand, my index is a 2, so I can really say that this is x squared times 1 minus x squared to the 1/2 power. Now hopefully you also notice, just like in the last example, I have a variable times something else with a variable. I have two functions being multiplied. And as soon as I see that, I know that it's going to be a product rule. But now within that product rule, there's a quantity to the 1/2 power. So that's going to be another chain rule inside a product rule. Are you ready? Maybe you can pause the video and try this one first by yourself, kind of following what we did on part A. See if you can apply it to part B. All right, I have the first times the derivative of the second, which is a chain rule. I'm going to bring the 1/2 forward. I'm going to keep my inside the same. I'm going to subtract 1 from the exponent, and then I'm not going to forget to multiply by the derivative of the inside, which is negative 2x. That's the first times the derivative of the second, plus the second times the derivative of my first. Don't forget the last piece of your product rule there. All right, now that we have that, the rest of it is just some algebra manipulation. So we're done with the calculus part. All we have to do now is the algebra manipulation. But sometimes, a lot of times, this is the hardest part. So here we go. We have one big term here that we need to try to combine some like terms. If you notice, I have a couple of different things. I have a negative exponent, a quantity raised to a negative exponent that I want to bring down to the denominator, right? And then I have a couple other pieces that I'm still being multiplied by. In my numerator then, I have an x squared times a 1 times a 2x. If I have an x squared times 1 times a 2x, don't I have a negative 2x cubed in my numerator? In my denominator, I have 1 times 2 times 1, which is just a 2, right? And then that whole quantity that I brought down to the bottom so that I can make that exponent positive. You might also notice that I can reduce a 2 from the numerator and the denominator because they're not connected with a plus or minus sign. They're just multiples of, factors of. I can reduce the top and the bottom by 2. So my first term ends up looking like this. Negative x cubed over 1 minus x squared to the 1/2 power. Excuse me. Now let's look at our second term over here. It looks like I have positive exponents already. I have a 2x on the top along with that 1 minus x squared to the 1/2 power. My denominator is really just a 1. Oop. So it looks like this. Now I want to add these fractions together. Remember that eventually we're going to have to do more stuff with these derivatives. So we want to try to take these fractions and combine them into one fraction with a common denominator so I can eventually set them equal to 0 and figure out where the derivative doesn't exist. We'll talk about that in the next chapter. But we want to take these two fractions and add them together, which means we need a common denominator. If you notice though, the second fraction only has a denominator of 1 and it needs a common denominator, just like the first fraction has a denominator. So the first fraction has the quantity 1 minus x squared to the 1/2, but the second fraction doesn't. So I'm going to multiply both the top and the bottom by that 1 minus x squared to the 1/2 so that both denominators are the same, so that we have a common denominator. When I do that, in my numerator, I have a negative x, ooh, that really covered that up, didn't it? Sorry. I have a negative x cubed plus I have a 2x, and then if I take a 1 minus x squared to the 1/2 and another 1 minus x squared to the 1/2, those bases are the same. And so when I multiply things with like bases, do you remember what we really do with the exponents? Yeah, we add them. So 1 minus x squared to the 1/2 times 1 minus x squared to the 1/2 is really just 1 minus x squared to the first. Don't forget you have a 2x in front of it as well. So you have a negative x cubed plus a 2x times 1 minus x squared to the first power now. I can go ahead and distribute the 2x through, and so my numerator is really negative x cubed plus 2x minus 2x cubed. You might notice that we have some like terms there. The negative x cubed and the negative 2x cubed really make me a negative 3x cubed plus 2x in my numerator over that common denominator. Remember that common denominator that we had to get? Of the 1 minus x squared to the 1/2 power. All my like terms are combined. I have a nice cute numerator and a nice cute denominator. This is my derivative, but I had to do product rule with a chain rule and then lots of fractional algebra stuff in there, right? All right, make sure that you practice those. Those do get a little bit more challenging as we go through. So make sure you practice all of your different types of chain rules, and then we'll do a few more here in a little bit that are also a little bit funner.